Now, having obtained equation for delta theta and an equation for alpha, we're going to eliminate omega f from these two equations, just as we would have eliminated VF from these two equations to get a new equation of motion. That we call our third equation of uniformly accelerated angular motion. And then eliminate delta t from the same two equations to get the fourth. Also, calculus definition of omega and alpha. What are the calculus definitions of your angular velocity and angular acceleration? Okay, you should pause, and while we're paused, up comes the board with the answers. Okay, you should have gotten these. First of all, just to summarize the equations of uniformly accelerated motion, and I'm not going to work these out for you. They've been worked out. If you have a problem with it, let me know, and I'll be glad to work them out again. But, or at least refer you to where I worked them out before. Here are our four equations of uniformly accelerated motion as they apply to intervals. Now, they could be also written as S of t equals VF plus V naught over 2 times t. If you want to talk about the position function, VF of t equals V naught plus AT, where V naught is the velocity when t equals 0. And since we're not talking about an interval, we won't talk about a VF here, okay? Or S of t equals V naught t plus 1/2 AT squared, VF squared equals V naught squared plus 2AS. Okay, and all these come from the calculus definition as well. And this is the interval concept. This is the functional concept. Okay. In any case, the equations you get for uniformly accelerated motion are obtained in exactly the same way the equations for, did I say uniform? Okay. The equations for uniformly accelerated angular motion are obtained in exactly the same way as the equations of uniformly accelerated linear motion. That is, we get our two equations, which are just rearrangements of the equations we obtained earlier from the definitions of velocity and acceleration. And here we eliminate VF from the two equations, and we get this equation. We eliminate delta t from the two equations, and we get this equation. Okay, well, over here, we do the same thing. These equations are exactly analogous. Where you have delta S, here you have a delta theta. Where you have a V, you have an omega. Delta t has the same notation in both, and where you have an A, you have an alpha. And these equations are obtained from the equations in the form we had them in the preceding. Again, by a very simple algebraic manipulation, we just solve one of them for delta theta, solve the other for omega f. One of them is already written in this form. The other one we can solve for delta f, and we get this. At that point, we eliminate omega f from the two equations, just substituting this in for omega f and simplifying, and we get delta theta. Well, I'm not going to read it to you. We get this third equation, and we eliminate delta t from the two equations. For example, solving this equation for delta t, substituting it in here, doing some simplification, we get this equation. Okay, so there are our equations. They're absolutely identical. If you want to not think about what these things mean and where they came from, you could just get in the habit of always, using these equations, which you already know, and letting these be replaced by omegas, S by theta, and A by alpha. I recommend you do this from a point of view of understanding, so you don't fall into the trap of relying on formulas that you don't completely understand. Although at some point you have to do that, you eventually get to the limit of what you can handle, and then you start using formulas. Okay, well, anyhow, And then the other thing I asked you to do for here was the calculus definitions. Omega is d theta dt, alpha is d omega dt. Okay, and I didn't write the analogy down here, but it's obvious. V equals ds dt and A equals dv dt, and you're familiar with that. Okay, in this case now, if alpha is constant, what do we conclude? You should pause and work out the repercussions of a constant alpha using these facts. We did it for uniformly accelerated motion. Goes exactly the same way for uniformly accelerated angular. We did it for motion in a straight line. It goes exactly the same way for rotational motion. Okay? Okay, well, hopefully you've done that. Alpha equals constant implies what? It implies that d omega dt is constant, which implies that omega is the integral of alpha, is an integral of alpha dt, which means that omega is alpha t plus some constant. And this constant can be identified by the fact that, well, if omega of t equals alpha t plus c, then omega of 0 equals c, because alpha t would be 0. So without losing any generality, we can write this as alpha t plus omega naught. And then d theta dt constant implies that theta is an integral of omega dt, which is an integral of alpha t plus omega naught dt, which in general is, let's stay over here, which in general is 1/2 alpha t squared plus omega naught t plus c. And since theta of t equals 0 would then equal c, c is identified with theta naught, so that's 1/2 alpha t squared plus omega naught t plus theta naught. So here we have two equations of motion that are analogous to this equation and to this equation. And by substituting variables and so forth, we can derive the other two equations very easily in the case where you have uniformly accelerated motion. And of course, the assumption that alpha is constant means that the angular motion is uniformly accelerated. So there's the development of what we know about the relationship between angular position theta, angular velocity omega, and angular acceleration alpha.